Hi, buddy. This is Mr. Folly, and welcome to Podcast 5.2, All the Laws, Two Bulbs, Mole Fraction, and Stoich of Gases. So there's a lot of stuff. Get your calculator ready, and let's hop into it. So Boyles' Law. Boyles' Law is PV, or P1V1 equals P2V2. And the graph of it is like this, pressure, volume. Charles's Law, which is T1 over V1 equals T2 over V2. It's directly proportional. Looks like this. Temperature, volume. Gay-Lussac's law. Let's see here. The graph I know looks like this. Gay-Lussac's law is P1 over T1 equals P2 over T2. Pressure, temperature. Or flip it around. Combined gas law. The formula is P1 V1 over T1 equals P2 V2 over T2. Now the other ones have been pretty straightforward on how to do it. This is the first one that's a little bit different. I want to remind you that for all of these, temperature has to be in kilkelvins. Temperature has to be in kilkelvins, and then Boyle's law doesn't have to deal with it, so that's kind of nice. So this one also has to be in kilkelvins. Sample, a bike tire with a pressure of 103.4 kilopascals, a volume of 944 milliliters, and a temperature of 22 degrees Celsius. Ooh, that's a dirty word. 22 plus 273 equals 295. I don't even want to look at that. Warms up 5 degrees, so that means my final temperature is going to be 300 Kelvin. And it inflates 10 milliliters, which means my final volume is going to be 954. When it is ridden quickly downhill, find the new pressure. So here we go. P1. Now I'm going to get the new pressure in the same unit it was given to me in. And this has died for me, so I'm going to have to take a little break. Oh, let's see. Sometimes I just hop to the next slide. It'll come back, and it did. Maybe it'll come back here. Come on, come back to me. Okay. Well, it is clearly not. So I'll try a little Dalton's law action. Dalton's law, adding gases adds pressure. So if I have pressure of O2 in a container plus pressure of H2 in a container plus pressure of SO2 in a container, that's going to equal the pressure total. So pressures are additive. Okay. Oh, look, here we go. Find the new pressure. So we've got P1. I'll hop back to this, I guess. P1 is 103.4 kilopascals. Check. V1 is 944. Now I don't have to change these units because it'll be the same on the other side. I do have to change the temperature though. 295 equals P2, which is what I'm solving for. V2, which is 954. I'm sorry about this, by the way. Over T2, which is 300. P2 equals, calculators assemble, 103.4 times 944 divided by 295 times 300 divided by 954 is 104.1 kilopascals. So notice the pressure went down a little bit. Okay, so the volume got bigger, which would reduce the pressure. The temperature went up, which would increase the pressure, but the volume change 1. Dalton's law. Oh, this was here a second ago. Adding gases adds pressure. Collecting gas over water must subtract water. So one way that we collect gases, or we do a reaction, we have a little tube that will then go into a bucket of water and into a test tube. And we will end up with a thing of water in this bubble. We'll push this guy down. Now typically we have to push this thing to where our water level is. Let's change my water level here. Make our water level even. And that gas thing bubbles out here and we have an even water level. That's important to have an even water level because that shows that the pressure inside the tube equals the pressure outside the tube if the water levels are even. Okay. Now if I have a pressure here, let's say I'm collecting hydrogen gas. In here I have hydrogen gas because you can see I bubbled it in there. I also have H2O gas. A little bit of water vapor always sneaks in there. So if I wanted to find out if I had an unknown gas, I can use the ideal gas law, PV equals nRT, if I wanted to do something like that. But this pressure inside equals the pressure outside. So if the pressure outside was 1.31 atmospheres, you'd think the pressure inside would be 1.31 atmospheres. That must be the pressure of hydrogen, but it's not. 1.31 atmospheres equals P total, and P total would be P total equals hydrogen plus water. Now, the pressure of water is small, but it is important. It's enough to calculate. Here's a sample question. Student collected a sample of hydrogen gas by the displacement of water as shown by the diagram above. Hey, I just drew one of those. The relevant data are given in the table below. Volume of the sample is 90. Cha-ching. Temperature, ooh, I hate you, temperature, 298 Kelvin. Again, I added 273 to it. Atmospheric pressure is 745. Equilibrium vapor pressure is 23.8 of water. So what that means is this pressure inside is 745. Except for I wrote 755. It's 745. Okay. Calculate the number of moles of hydrogen gas collected. So if I want to find the moles of hydrogen, I want to do PV equals nRT, but I need to have the right pressure. Okay. So my pressure here, that total is 745, but the pressure of hydrogen is 745 minus 23.8. Total minus hydrogen, minus water equals hydrogen, which is shown as pH2. So 745 minus 23.8 is 721.2. Now, when I use PV equals nRT, R is a big pain because R is 0.0821 liter atmospheres per mole Kelvin, which means I need to obey all of those units. I need to be in liters, need to be in atmospheres, need to be in moles, need to be in kelvins. So the 721.2 millimeters of Hg I need to change into atmospheres. And I do that by dividing by 760 millimeters of mercury. Okay, so calculate the number of moles. So I'm going to do PV equals nRT. So I'll write it up here. PV equals nRT. Pressure is 721 over 721.2 over 760. That gets me into atmospheres. The volume I have is 90 milliliters. That's 0.090 liters. Remember how R is bossy pants. N is our moles. R is 0.0821. And that's just a constant like pi that gets us the right answer. And our temperature is 298. Do that math and you get the answer. Calculate the number of molecules of water vapor in that gas. So that would be whatever my answer to A is, times molecules of water vapor. Oh no! What a pain, because that's not hydrogen. Now I've got to figure it out for hydrogen. Hydrogen's pressure, water vapor. Water vapor's pressure is 23.8, so I need to do PV equals nRT for water. So my pressure is going to be 23.8. No, it's not. Over 760. Volume of water is that same volume, 0.090. Equals N 0.0821 times 300. I get N for that one. I'll actually solve this one. 23.8 divided by 760 times 0.09 divided by 0.0821 divided by 300 is 1.14 E negative 4 moles. And to get that into molecules, I have 1.14 E negative 4 moles of H2O times 1 mole over Avogadro's number, 6.02 E23 molecules. And my calculator tells me that is 6.89 E19. Which two gases deviates more from ideal behavior? Explain your answer. Water. More attractive? Hubba. Hubba. And bigger. Bigger. So it's more attractive. Avogadro's law. Whoops, I snuck that one in the wrong spot. Avogadro's law is moles over volume equals moles over volume. Notice it too is directly proportional. 22.4 liters does not equal 1 mole. It can, but it almost never does. It does equal 1 mole at STP, but we are never at STP. Not at STP. We are almost never ever at STP. Now I put this here because is it possible that you can be in Disney World in a perfectly bright sunshiny day? Oh look, here's the parade going on. Oh look, here's the parade. And look, here's Snow White. She comes up, I don't know where I'm going with this, and gives you a little smooch on the cheek. Oh, I'm blushing, how wonderful. Oh, I just got a little crown on. And the dwarves come and they pick you up and sing for he's a jolly good fellow or feather. And here comes Tinkerbell flying around going, ooh, there's a little magic wand. And all these other great things happen. And someone gives you a Mickey Mouse ice cream bar. It could happen, but it's not going to. So it is possible that it could equal 1 mole, but never, ever, ever expect it. Bold problems. Pressures are independent and additive. So that means the pressure of hydrogen doesn't care, cares less, I guess doesn't care, no care, if other gases are present. Now, if I ask you why, it's because those particles are so small and so unattractive, ideally, that they do not interact with other ones. A bulb apparatus shown below has one end with 2.50 moles of gas and 3 liters. Here's 3.00 liters, 2.50 moles. And the other bulb with 3 moles and 4.5. 3.00 moles, 4.50 liters. Calculate the final pressure when the stopcock is opened. So this guy's going to open up, and these guys go and mix up. So what's going to happen is I'll call this gas X, because I don't think it says, and this gas Y. So for X, I'm going to do PV equals PV. This is for X. So my first pressure, oh man, actually, you know what, I'm going to do this a little bit differently. What happens is, for this, is I'm going to calculate my total moles, right? So if my total moles are 5.50, oh man, this is a bummer. I don't think there's a shorter way to do this. 5.50 moles, and, oh yeah, there is, 5.50 moles in 7.50 liters. But I have a problem with that. Oh, that's a bummer. So what I have to do is PV equals nRT twice. nRT. So my pressure is what I have to find from this first part. So 2.50. I don't want to do this one. 0.0821. Temperature is 273. Oh, you know what? It doesn't say what it is. I'm skipping this bulb problem. How about that? Lucky you. Yeah. Ideal gas law. We've done this already. Went over it in class. So we can find it in ideal PV equals mass RT over molar mass. This is common. That I think is more common than that one. Or to find density. Now remember how mass over volume equals density? So I could make it PMM. I better write that better. Through cross multiplication, PMM. See, woo, woo, over RT equals mass over volume. Okay, V moves down. Molar mass moves up, this moves down. Mass over volume equals density. So density equals PMM over RT. I'm not going to do all these problems, I'm going to do a couple of them. The mass of 1.12 liters of gas Y is found to be 6.23 liters. The density of gas Y is, I'm not going to do that. Density is mass over volume. Not that one. Molar mass of Y is, okay, so if I know the density here, I guess I am going to do it. 6.23 grams over 1.12 liters. 6.23 divided by 1.12 is 5.56. We're going to go ahead and say we're at STP. Okay, so if I said D equals PMM over RT, the density is 5.56 equals the pressure, or I'm going to say at STP, 1 atmosphere molar mass over R, 0.0821. T is 273. Remember, that's the standard temperature pressure. Solve for molar mass, you get an answer. Okay? And this is where it's at STP, so as much as that doesn't have very much. 0.72 grams of liquid is vaporized at this, the atmosphere occupies that, empirical formula is that, what's the molecular formula? So what we're going to do is do PV equals mass RT over molar mass. Now why? How did I know that? Molecular formula is molecular mass. Okay, a pressure is 0.967. I'm skipping this one in case you didn't notice. Volume is 0.559. Notice how I am cautious to make sure my units agree with R. Equals mass 0.72. Notice how gases don't weigh very much. R is 0.0821. Temperature is not 110. It is 383. Surprised I let that one stand. Over molar mass. Then I do the math. Okay, here's the stoich for it, and then we'll be done. 2KClO3 yields 2KCl plus O2. Hey, look, a chlorate decomposed into a chloride and oxygen. Some of you have memorized that. 3-gram sample of KClO3, 3.00 gram sample. It's decomposed and the oxygen at 24 degrees Celsius and 0.1812 atmospheres collection. Notice the oxygen is collected of this. What volume of gas would be collected assuming 100% yield? So what's going to happen is I'm going to do 3 grams times dividing bar of KClO3. And then I have to go to the periodic table. So potassium is 39.1 plus 35.45 plus 48 is 122.55. 122.55 grams KClO3. 1 mole KClO3. But my handwriting's getting worse. And I'm turning into oxygen. 2 moles of KClO3. 3 moles of O2. And then I'll stop there. So 3 grams divided by, 122.55 times, times 3 divided by 2 is 0.0367 moles. And then if I want to find out what volume, I'm going to PV equals nRT it. And this is pretty common, just to slap a PV equals nRT on the end of it. Remember how we slapped a molarity equals moles over liters at the end of sum for solutions? This will be very common. I'm going to make my equal sign look better. My pressure is 0.812. My volume is what I'm solving for. My moles are 0.0367. R is 0.0821. Temperature is 24, no way. 24 plus 273 is 297. V equals whatever it equals. Okay. Mole fraction is just a fraction. So P total equals mole fraction 1, P1, plus mole fraction 2, P2. Okay. So this gives you the ratio. So notice how if I have gases that goes with this is just the fraction that goes with it. Maybe you have a problem? A vessel with a volume of 16.4 liters contains 2.80 grams of nitrogen, 0.403 grams of hydrogen, 79.9 grams of argon. What is the pressure? So what I'm going to do is I'm going to find the pressure of this, pressure of this, pressure of this, and add them all up. Okay? PV equals nRT. My pressure is what I'm looking for. Volume is 16.4 liters. That's good because I need to obey the other one. Oh man, 2.80 grams. I hope you're okay if I take 2.80 and divide it by 28, and this will give you the moles. That's 0.1 moles. R is 0.0821. Temperature is 298 Kelvin, and P equals 0.1 times 0.0821 times 298 divided by 16.4, 0.149. Next one is hydrogen. Remember, hydrogen weighs 2.02, so N equals 0.403 divided by 2.02 is 0.1995. Pardon me. So pressure, volume is 16.4, same container. 0.1995. R is 0.0821. Temperature is 298. Solve for this bad boy. Times 0.0821 times 298 divided by 16.4. And P equals 0.298. By the way, this will come out in atmospheres because of the R I chose. Argon weighs, oh man, I don't know what argon weighs. Silly periodic table. Argon weighs 39.95, which is half of this. This is 0.5 moles. No, it's not. It's 2 moles. Shame on me. 2 moles. So, P equals 16.4, same volume, 16, equals 2.0821 times 298. P equals 2 times 0.0821 times 298 divided by 16.4, and I get 2.98 atmospheres. So my total pressure is the sum of this, so 2.98 plus 0.149 plus 0.298, and I hope I get an answer here, 3.43. Woohoo! Woo! I'm so happy. I'm done. Guests are independent. You have to be able to know the portion that I do the math. I'm so glad it's over. Toodles.